Again, my name is Derek Pizarro. I'm a senior project manager with AST Environmental, and I'm welcoming you to accelerated cVOC remediation using BOS100 and CAT100 and the secret to DNAPL treatment. I do appreciate everyone's time. I know these are certainly crazy times for all of us, but I do appreciate you carving out about half an hour here for us. This is a third installment in the RPI Group webinar series. So if you joined us previously, we do appreciate your continued viewing. If you haven't joined us before, we can make some of those presentations available to you. After this, we can also ask that you look at our schedule here, and maybe there's something that piques your interest, expounds upon things you've seen our group present already this spring during our spring webinar series. And just as an overview, this is really an introduction to the trap and treat product line that RPI has developed. And then on the installation side, a lot of different methods, techniques, practices that we use from design to installation to performance monitoring that are going to help you improve the results at your site and client satisfaction, while also at the same time managing expectations. So here's a little bit of our overview. I do want to go back for 1 second. I obviously want to thank everybody involved here. Obviously, AST Environmental, my coworkers, RPI as well, who's hosting this webinar. And then we've also been fortunate to have guest speaker Aaron Peacock with Microbac Laboratories just last week. So I do appreciate the collaboration we have going on here. So thank everybody for their efforts, and thank you all for joining us today. Here's a brief overview of the RPI group if you're not familiar with us. If you are familiar with us, you've probably seen this tripod, this three-way circle of process that we've used for a good number of years now, probably about a decade. And this is really what encompasses our total group. RPI developed the technology. They also run the project support laboratory in Golden, Colorado. And then on the design side, you have AST Environmental, and then both AST and a number of authorized installers are part of our installation network. And that network is extremely important because, as you'll see through these presentations today, next week, and subsequently, that it's not just about having great technology, which this is, it's also about having it designed and installed properly. So this triumvirate of groups here is very important to this overall process. Here's a little bit about our footprint. I know a number of you on this webinar are probably doing work internationally, so there's definitely some footprint there as well. We've definitely expanded into Canada. We've got a great installer up there. We've done a lot of different applications up there. We'll talk about some of them as we go through this presentation, but we've definitely got a good footprint. So if there's some areas of the world you're working in, we'd definitely like to see if we can help you out there. Here's a roadmap for today. Just kind of a quick snapshot of where we're going. We're going to start with the technology, which expounds upon some of the things that our first webinar, which was regarding activated carbon as a platform for treatment. We're going to expound upon that a little bit, and then we're going to focus on BOS100 and CAT100, since we're focusing on chlorinated solvent, cVOC, other contaminant degradation today that really falls within those two products. There is another product, BOS200, which is not mentioned here, that'll be covered in a webinar next week with my colleague, Mike Mazzarese. In terms of typical applications, while we are dealing with slurry technologies here, it doesn't mean we're limited in how we can apply, how we can use them at a site. It's not going to constrain us from a lot of the source area treatments, PRB applications, plume bisection, et cetera, that you're used to accomplishing with other technologies. There is some additional design and planning that goes along with it to deal with some of those constraints being a slurry, but you're not precluded from using these in traditional areas where you would use other remedies. In that same vein, there are going to be applications out there where you would use these technologies in conjunction with another remedy. So, while combined remedies has become a buzzword in our industry recently, it's something that we've been doing as practitioners for a long time, and certainly don't think that because these are slurries that you're precluded from using these in a multitude of different fashions. So let's focus on the technology. We're going to revisit the trap and treat concept, and that's primarily just to discuss the activated carbon component of these two products we're dealing with here today. Some of that is to dismiss, some of the preconceived notions or the misunderstandings of using activated carbon as a tool. Probably the biggest thing to note with RPI's products is this is trap and treat. It's not just trapping. If you would like to trap a contaminant, sequester it away in the subsurface, you could use standard activated carbon. Everything we're doing here today has a treatment component to it. And that's really our goal. We don't want to sequester something and leave it in the subsurface to be dealt with biologically for years and years and years and years. This is something that we want to go in and concisely treat and have a mechanism to do that with. So be it known that this is the only portfolio on the market that has a treatment mechanism installed on activated carbon. And with that, if you haven't used activated carbon before, it is a really powerful tool. Probably the most important part about installing a carbon platform into the subsurface is that we're immediately going to remove groundwater mass. You would see that with any type of activated carbon installation. However, it's the treatment component that goes along with that really facilitates the powerful activated carbon platform. When these go in situ, we're immediately disrupting the soil groundwater partition, and we're also using groundwater as a transport mechanism to drive soil desorption of our absorbed contaminant mass. And that's really the key to these technologies, is getting that soil mass off into the dissolve phase and moved onto the activated carbon. Because if we can't transport it to the site where we have treatment, we can't do anything other than trap it. So activated carbon products, while a very powerful tool, definitely need a treatment mechanism associated with them. If you're not too familiar with activated carbon, just wanted to cover a few things, again, clarifying what we're doing here at RPI Group. We are using food-grade coal-based activated carbon, and the reason for that is a lot of the contaminants that you deal with, whether they're chlorinated today or possibly another contaminant covered in another webinar, have very high demands on the carbon platform. So you want very high carbon absorption isotherms. And with that, we use coal-based activated carbon because it has much higher absorption isotherms than even cellulose, wood, coconut, other things that are available in the marketplace. So anytime you're putting a product in the ground, you want the most bang for your buck. So that's why we're starting with coal-based activated carbon. I put a note in there. We always use virgin activated carbon. I know from a sustainability standpoint, a lot of us would like to use regenerated activated carbon. Unfortunately, due to typically high heavy metals content in regenerated activated carbon, that's just not something we can do at this point. So all these are virgin activated carbons. And just as a note, I really like that picture there on the right. When you're looking at the powerful platform that is activated carbon, there's a lot of surface area to work with. So I really like that note there that just 5 grams of activated carbon has the internal surface area of a football field. So that's a great way to think about how powerful this tool is. The second thing in dealing with activated carbon is we have to concern ourselves with not just what contaminant we're treating, but other contaminants in the mix and also their concentrations, their respective concentrations. So a lot of times when you work with RPI Group, you're going to hear us talking about acquiring speciated data, whether it currently exists for your site or developing it as we move through a RDC, remedial design characterization, or further investigations to augment your CSM. But just as an overview here, I like this example here comparing the concentrations of vinyl chloride and cis-DCE and the capacity demands they would have on the activated carbon platform. And you can see just at 10 micrograms per liter, there's an order of magnitude difference on the capacity that carbon can absorb between vinyl chloride and cis-DCE. So again, this is just a very rudimentary example, but it's a good example of how important designing the carbon platform capacity is for your site. So now let's talk about BOS100, our first product we're dealing with here today. This is abiotic dechlorination. And what we're dealing with here, as you can see there in the bottom right there, is a beta elimination pathway. So we're not going to step through a progressive dechlorination process. We're going to slide into the beta elimination pathway and take it all the way down to ethene there at the end. A little bit more about this product. I mentioned these are food grade activated carbons. We start for BOS100 with granular activated carbon, and then we impregnate it with metallic iron, giving it about a 6.5% by weight combination. Now, I do want to say that this combination is really a fusion. It's not a mixture. And I'll talk about that in my next slide, but that's important to note because if you combine activated carbon with any other type of treatment mechanism you would like to utilize in situ, you're going to sequester it away on the activated carbon. There's no treatment mechanism available within a plain activated carbon. So you're removing it from the one you're installing it if you just co-mix it. So that's an important thing to note, that you must have your treatment mechanism directly on the activated carbon platform, which is really why we're here today. The next thing we get asked a lot is, well, you're talking about metallic iron. How does this compare to more traditional iron treatments on the marketplace today? And this is really where I'm going to drill down on using the two in conjunction with each other and the fact that they are one product. It's a fusion of technologies, literally. And what you see here in that first bullet point, activated carbon, we need this to drive degradation rate. That's the most important part of this. When you use activated carbon, you're concentrating your contaminant on the activated carbon platform, which means you can enhance your degradation rate. The second thing to note is because this is carbon fused with iron, they become one and the same. So this becomes an enhanced electron transfer system. So you need the two working in conjunction with each other, not just to trap the contaminant, but to treat it. In terms of the availability of iron, whether you use a traditional metallic iron amendment like ZVI or BOS100, we get asked a lot, what about surface area and reactivity? What about longevity? And I call out a couple of those points here in the slide. In terms of longevity, we've got a lot of data available to us at this point showing that we can go a decade or more in terms of performance and longevity of that iron in situ. So we're not going to have some of the depletion and oxidation issues that we would with other traditional iron amendments. So the next product we're going to talk about is CAT100. Think of this as an improvement upon BOS100. Think of this as a marriage between BOS100 and ERD. And this kind of depiction here on the right really shows you what's going into the mix. At its heart, we're starting with BOS100, and then we're adding electron donors, yeast extract, and then two different bacterial consortiums. Each of those does two different things. One focuses on the generation of electrons, and the other focuses on a concert of degradation of the cVOCs in situ. So think of these as, while they are originally separate entities going into the mix, when they get into the mixed tank and installed in situ, this is a concert of activities working together to drive expedited cVOC degradation. And so I'll explain a little bit of that process here on this slide. Aside from electrostatically binding the compound that you're dealing with to the iron on the activated carbon, we have to generate electrons. Because if we don't generate electrons, we're going to start depleting our iron. And the way we preserve the iron is this generation of electrons by the fermentation of typically food-grade starch, occasionally chitin, by our first facultative blend of bacteria. And really, people ask us a lot of times how we came up with the naming for this product. Well, CAT100 is really short for catalyst, because that's what this is. That fusion of iron and carbon together works just like a conduit in the walls of your house, your office. It's transferring the electrons we're generating to the site where the contaminant is bound to the structure, and that's our degradation process. And what we're doing here is, by the continuous generation of electrons, we're transferring them into the structure of the activated carbon and iron. This is our electron pump. So while food-grade starch is going to very slowly break down over time, it's going to be a great electron donor for this system. If you were to continue to keep those starch levels monitored and bumped up, you're going to look at this as essentially a electron pump in perpetuity. You could theoretically keep this system moving. That's how powerful this is. So again, we're not depleting the iron here, we're preserving it. So this is really good for sites where you've got DNAPL, mixed plumes. This combination, this facultative blend of bacteria can be adjusted based upon your site to handle, if you're doing more than just cVOCs, if you're doing SVOCs, even chlorinated SVOCs, and other compounds as well. So this is something that we can tweak through the design process, through the site assessment process, to really make sure it's a good fit for your site. We've used CAT a lot for source applications, but we've also started to use it in the last 4 years on PRBs as well. We do have some case studies we can provide for those, but it is pretty versatile. We find a lot of uses for it, especially when we have significantly impacted areas or plumes that we have to bisect. And the last thing to note in this section is, I talked about having a treatment mechanism combined with the trap of the activated carbon. Again, it can be very hard to determine, at least at the outset, post-installation, what type of treatment you have going on. Because if you inject activated carbon into the subsurface, you're going to clean up your dissolved phase. You're going to see depletions in your groundwater monitoring, but how do you actually know you've got treatment going on? So we've come up with a number of ways to do that here. These are not, things that we invented ourselves per se, but these are typical monitoring parameters that we use for a lot of projects. Total mass, we don't always have the ability to go out and take a probe back out with us post-installation. Sometimes we do. That's a real easy and nice way to go about monitoring treatment. Dissolved gas generation, volatile fatty acids. There's some other parameters we use for both BOS and CAT100, also BOS100. All those can easily be collected and monitored in the field through your VOA vials post-installation. So it's not an invasive way to go about this. This really complements your post-monitoring analysis. But here's some of the things we use. More recently, we've also started working with microbac laboratories. We've done some CSIA analysis and other microbial diagnostics. That's certainly something I would implore you to reach out to both Aaron Peacock and Scott Nolan about. They gave a great presentation for our first two webinars about some of this. And if that's something you're interested in for your site, they could talk to you about that. So we talked about the importance of both product and design and installation. And here we're going to focus on the design component. And just earlier this year, ITRC released their Optimizing Injection Strategies and In Situ Remediation Performance document. It was very comprehensive, very well done. And one of the most important things for us we saw in there was the description of remedial design characterization and how it's a great tool to use. Shortly thereafter, Scott and I talked about this on the phone, and he gave me this quote, and I really think it's salient because a lot of the times that we have sites that become recalcitrant, it's because we don't have an accurate snapshot of the subsurface. We have a CSM, but maybe it's predicated upon limited soil data, long well screens. You're trying to use, high resolution tooling outside of the way it's meant to be used, or you're trying to interpret an electronic output signal as a quantification of impacts in the subsurface, which you can draw correlations, but it's still at the end of the day, you have to use wet chemistry to determine it. So one of the reasons I like this is because it shows you the value of doing a little bit more work up front with an RDC, which is something we've been doing here at RPI Group for a decade now. And this is borrowed from ITRC. Again, it's in that recently published document. And I think it's just a nice example. If you visit it, it's a nice example of showing you how you end up with both cost and time savings by spending a little bit more upfront, or you can see in that shorter interval of time mid-project, that gets you to a completion and time savings a lot quicker. So when you hear those of us within the RPI group talking about this, it's not just to take more soil samples, it's not just to spend more time on site, it's to gather an accurate snapshot of what's going on in the subsurface so we can assist you with the design. With the design, we get asked a lot, can these products handle DNAPL, if it's BOS200, LNAPL? We talked in a previous slide about how we go about doing that, but at the end of the day, the reason I brought up the RDC is that is the way we deal with DNAPL. If we know where it is, if we know the concentrations we're dealing with, we can start to look at ways to design around a treatment design and plan for that site. A lot of that revolves around knowing the mass, location. Some of this will be covered in an RPI or an RDC specific webinar coming up in a couple weeks. But this is really how you get into understanding the treatment mechanisms available to you in situ with these products, and then finding a way to use them on your site. One thing I like to call out here is RPI has available to our clients the project support laboratory. We get asked a lot, is there a cost with sending them samples? And there isn't. And I know some sites we've sent a lot of samples. We had a site up in Michigan just last year in 2019, we sent almost 1,200 samples to RPI's lab. That was all conducted at no cost to the client, but it helped them come up with a design where they were able to address a very long chlorinated solvent plume with a source area and two-stage PRB treatment design. So Again, this is all things that you're going to talk about with us when we're working together, and this is one of the ways through utilizing RPI's Project Support Laboratory that we help you minimize your costs through that RDC. In terms of installation, again, I mentioned at the outset, these are slurries, so they will require different equipment. They will require different training for the field staff. Through the RDC, we have a precise injection plan, which helps us. But at the end of the day, the installation is still the most important part of the overall design. So working with the RPI group, we've developed best practices. We've developed techniques. We've got specific equipment that you won't find off on the shelf at Ferguson or Home Depot, Grainger, places like that. These are custom-built systems meant to put slurry in the ground. And as an example here, we have a couple pictures on the right there, a couple cores. You can see the first two there are some finer grain materials. You can see the distribution there. If you go down to the bottom picture there, you can see when we get into coarser materials, we do a slightly different injection, almost a co-mixing method there. A lot of this will be covered in the injection webinar, or you can reach out to us separately. But I just wanted to put this in there to show you what we're dealing with in the subsurface when it comes to installation. And the last thing I want to focus on with installation is we get a lot of inbound inquiries talking about PRBs these days. PRBs have certainly reached a point of modernity in our industry. They are very good tools. They can be used in a multitude of forms or fashions. If you're talking with us, you're probably looking at injecting a PRB. But obviously, you can see there from that picture on the right, if you can do this with yellow iron, you could accomplish that as well. Here's a little picture grid of injectable PRB. Most times, we're going to be looking at 3, 4, or 5 curtains within that PRB. Again, it's all about contact, but with the proper design, an injection plan, and the right products from the RPI group, you can accomplish the exact same thing you're doing with a trenching application with yellow iron. You can accomplish it with an injectable PRB. The next thing I want to touch on real quick is the pre-drill example. This is something the RPI group's been doing for a long time now. Think of pre-drill as when we can't access targeted depths or the top of bedrock that we need to or want to, based upon either natural or man-made conditions. Pre-drill is great for cobble zones, glacial till, urban fill, anywhere where you get refusal just using a standard DPT rig. Roughly what we're doing here is we're pre-drilling the site using either augers or sonic to achieve our targeted depths, backfilling with hydrated bentonite. And then we actually use a DPT rig to go through that bentonite to inject in the formation. This has been used at sites with some of the issues that we just talked about a second ago. We've also used it in heaving sands. You can see there's a note there. We recently did a DOD site in South Carolina. That was the heaving sand site. We pre-drilled using sonic to 180 feet plus, a lot of locations there to install a PRB for chlorinated solvents. Again, I ask you, if this is something that interests you, join us on May 12th for the pre-drill webinar. All right, so we're going to move over. We're going to look at a couple case studies here, and then we'll take some questions. First one here, our former military site. This project had an objective where we needed to evaluate the effectiveness of BOS100 for the remediation of TCE and potential DNAPL as well. We had saturated soil. We had a perched groundwater table. We're specifically looking around, see in a second here on the map when I pull this up. There it is. You'll see that we're dealing with an area around MW18. So focus on the next slide around the grid that shows up in the upper right. Part of this approach, we had DPT refusal, so I'm including this as a example since we just talked about pre-drill. Pre-drill is something that we used here at this site, both to achieve depth but also distribution. In terms of what we did here at the site, we installed 4 monitoring wells. We also used a solvent continuous multi-channel tubing installation. That's a multi-level well. Some other challenges we dealt with, there was a historic borehole right in the center of where we installed a 5-foot grid for injection. Unfortunately, it wasn't abandoned well, so we addressed those issues on site while we were completing some of these injections, trying to improve its abandonment. to minimize any daylighting that would come up through that improperly abandoned borehole. We also did a pilot test. This was a couple years ago now, but the idea is to do some long-term performance monitoring and then have a full-scale project funded at some point in the future, which we just got notice recently that we are going to do. In terms of this pilot, which we conducted in 2016, though, you can see from the upper right, we varied our grid spacing. This is to evaluate distribution, product loading, and efficacy of that combination. Again, this is just a pilot scale phase. We were able to get really good distribution, though. We had extremely good flow rates. You can see there from 35 to roughly 85 GPM. And then here we are on this slide here. We can talk about the performance monitoring. Again, we're at 1,300 plus days here, and we see significant reductions. I like this graph here that we've put together because while that initial precipitous drop-off would be indicative of using an activated carbon platform, you couldn't achieve this significant degradation and reduction there over that term period without the combination of the activated carbon and iron. So this is exciting. This is going to be reactivated this year, hopefully for a full-scale event. And this was a really good pilot for us at this site. And I'll close with a brief overview of a former manufacturing site in the Midwest. I'm going to look specifically at this interim remedial measure we conducted. And you'll want to focus here on that blow up. MW71 is close to our source area there. It's a former degreaser. MW63, while it's still within this IRM area, is another measuring point for us. As we go through this, we're going to look at some concentration data, some biological activity, and some other parameters we use to monitor performance in subsequent slides here. But just as a brief overview here, we had significant saturated soil, groundwater impacts. Immediately due to those concentrations, we selected CAT100. From our design there in the middle of the screen, you can see that's 215 direct push points. Again, that sounds like a lot of points to install, but we're not limited by how fast we can pump. We're limited by how much we can probe. And by that, I mean pumping times when we're doing these injections are on the order of 20, 30 seconds, whereas traditional injections take a lot longer when you hook up to an injection well or other form of injection. What we're doing here is we're probing as fast as we can. We're doing our injections. So this is distributed typically at every 1.5 or 2 foot intervals, and we're doing this on 5 foot centers. And within that area there, we did a little more than 11,000 pounds of CAT100. So let's look at some performance data there because we needed to tamp down those cVOC concentrations to limit my contaminant migration. As you can see there on the left there, we have receptors there in the form of row homes immediately off site across the street from this location. So let's see how we did there. So here's MW71. You could see an immediate post full-scale injection, an immediate precipitous drop-off of TCE. And then roughly in a 4 or 5 month period, we really start to see the biological degradation of the CAT100 kickoff. And this has been recently updated. Obviously, you're seeing some pulses here. Now, when we see these type of graphs, we don't consider these spikes here to be rebound. That's not the way this technology works. When we see these minor spikes in concentrations here, we know we're getting transport off the soil. We know we're finding void spaces where maybe some DNAPL is located. Again, we want to bring it into the groundwater to use that again as our transport treatment mechanism, to bring it to the activated carbon where we have that mechanism available to us. So this is some really good data here. Another thing we do commonly is chloride. That's a really simple parameter. We talked about that earlier. Here's that graph for this site. And then I'm going to end with the biological signature for MW71. A couple of things to note here. You've got really healthy, strong, sustained bio. And this is only with one injection. And you can see here we've bumped up a lot of these different colonies here, a lot of these different cell counts we're dealing with. If you look at some of the genes, we've got BC degraders that went from next to nil to now we've got spikes that are into the healthy cell count range there. So this product, CAT100, did a really good job of not just increasing our biological degradation activity in the subsurface, but also depleting our cVOC concentrations, both dissolved and absorbed as well. So that'll be it for me at this moment. I do appreciate your time that you spent with us today. We're going to open this up for Q&A. In addition to myself, I'm also inviting Dwayne Guilfoyle, who's president of AST Environmental, and Mike Mezzarese, my colleague, who's a senior engineer out of Colorado as well. And they've been monitoring the questions in the chat, and we can look at that now.
I got some questions that came in the last half hour. So the first one is related to PRBs and sort of, discuss the ideal concentration range for PRBs, and then as sort of a second piece of that, would you recommend, in what situations would you use BOS versus CAT in a PRB application?
You want me to take that, Derek?
Sure. Yeah, you just went through this at one of your sites.
Yeah, it's fine. I'll give you some examples. So related to concentration, so we've installed PRBs to address low dissolved concentrations for one of the PRBs that are provided as an example in the PRB webinar is installation that was completed in North Carolina, where we were addressing around 200 ppb or microgram per liter of TC that was upwelling into a creek. And then recently, we just installed a PRB up in Ann Arbor, Michigan that Derek was talking about, that we did a large remedial design characterization where concentrations of the TCE coming into the PRB were in the magnitude of 15,000 microgram per liter. So looking to handle high range, low ranges, it's all about just calculations of the overall demand on the iron and the overall isotherms related to speciated compounds from the mass flux coming into the PRB itself. The second question was, or part of that was related to the use of the BOS100 versus CAT100. CAT100 can be used, and it's all more driven by the seepage velocity. So the CAT100, with the fact that you're using a biological process to feed the electrons driving the overall oxidation on the iron, that we would use it as a precursor to an actual BOS100 PRB that would be on the down gradient side. So you can use CAT100 in conjunction with the BOS100 as kind of a treatment train approach, where you're using the CAT100 to handle some larger concentration mass and then have a polishing of effect with the BOS100 PRB.
All right. Thank you. Here's another one that came in. Would you consider CAT100 more applicable for anaerobic or aerobic aquifers?
It doesn't matter. Again, the site in Michigan, we were dealing with an aerobic aquifer, and once you put the product in the ground, it's going to scavenge all the oxygen and drive it into an anaerobic state. That was a very high flux aquifer, DOs in the range of 3 to 4, and like I said, immediately, as soon as you put in the activated carbon, a part of the CAT100 or the BOS100, it's going to scavenge the oxygen, specifically in the CAT100, as part of the overall biological process and driving it into anaerobic. So it doesn't really matter.
Okay. All right, so there's another one came in regarding really time frames, and so it says the 2 case studies show positive results, but only a few years out. Will this continue indefinitely, or do you need to reapply after some period of time? And the example was, say, 10 years.
It's all about the total mass of the formation. So if you do your calculations, if you do a proper remedial design characterization to determine the total mass in the formation, then you can install enough treatment mechanism in place in order to be able to handle that, whether that you are relying specifically on the abiotic process with the BOS100 or whether you're looking at more of a combined approach with the CAT100. So the longevity can, like we said, we have data related to, the use of the BOS100 that, we know that the iron is going to be good for decades. It could be longer than that. That's just the evidence that we have right now from the testing associated with that. So it's really driven by the total mass that you determine is in the formation, and to make sure that you have enough treatment mechanism in place. So And that's the power of the product. You can design many different ways to where that for a PRB, you may decide you want to last for 5 years. You put enough, treatment mechanism in place to be able to handle that period of time. You may decide that I've got X amount of money to spend, for an owner does, and I'd like to see a 70% reduction in mass, and then, later down the road, address the remaining portion. So it's truly just driven by the total mass present.
Okay. I'm going to go ahead and combine two questions here. So one is really regarding the depth limitations, and then there's another question that's somewhat related to it, into what situations have you used the pre-drill method before?
So your first question, Mike, the depth limitation?
Right. So, depth limitations on this is the question is specifically for DNAPL, but obviously it would be for any situation. Then there's a second question that's tied to the pre-drill. So I think you could probably handle those together.
Did you want to address that, Derek, or do you want me to handle it?
Well, I was going to jump in on the pre-drill aspect there.
Sure.
I mean, a lot of times, in my estimation and experience, when we use the pre-drill method, I don't really. We've tested this at extreme depths. We used that example there of the DoD site in South Carolina. But I would say most of our sites, especially in the Piedmont area, Eastern Seaboard, we're typically going to hit bedrock somewhere between, if we're using this method, somewhere between 30, 40, and downwards of 100, feet. So, we're not really extending or pushing the limits of the capabilities of these sonic probes, which is typically what we're using when we get down that far. So maybe the best way to answer that comment is, typically these days we're switching over to a sonic rig instead of maybe solid stem augers or hollow stem augers. We've started to use a lot more sonic for that pre-drill method because of its speed and because of its access, and we're not really limited depth-wise on it. What was the other part of that, Mike?
I would follow up with that, Derek. I agree with you. I think it's all driven by the limit of the equipment, and at this point in time, we've not maxed that out. I mean, we know that we can get to 180 feet, an overburden setting. We know what we can do in a bedrock. I mean, open boreholes and stratopacker assemblies. I mean, we're really kind of unlimited related to that. But in an overburden setting, I mean, like Derek's saying, we've gone to 180 feet. And we're pushing back through that with a regular 77 size probe. If necessary, we could bump that up to a 3230 to drive back through the bentonite, and like Derek's saying, it's really driven by really the limitations of the pre-drill of the sonic unit or whatever other method that you're using.
And I would add to that, Dwayne, maybe the one thing we do adjust though is the bentonite mix that goes in. At some of these deeper depths, we might add a little bit of grout to improve the overall.
Well, like at the Shaw Air Force Base project, we actually used bentonite pellets and then went to a slurry. So it was a combination. So you're right, Derek. You may change. You're not going to just you're not using chips at 180 feet. I mean, it's a combination of, bentonite pellets, coated pellets, slurries, whatever's necessary to still create a seal when we drive back through it, but allow us to be able to penetrate to get to that depth. What was the second part, Mike, to that question?
I think you guys answered it. It was just, depth limitations. And so I think you guys handled that with the pre-drill,
Okay.
with the pre-drill response. Okay. So we've got a few more minutes here. Just one comment. We probably won't get to everyone's questions, but we will follow up with you afterwards with responses, the ones we can't get to. But we'll try to get a few more in here. Looks like we've got about 4 more minutes. So one question is, are you eliminating soil source areas in addition to groundwater? So are you eliminating soil mass as well as groundwater mass for source area remediation?
Absolutely. It's the only way to clean the whole site up. So that's the power of the product. Our goal is drive that, like Derek said, to drive the mass off of the saturated soils onto the carbon for ultimately treatment. We know that in order to close these sites, because they've been staying around for so long, is because that's where all the mass resides. And going back to the remedial design characterization, that's the importance of grabbing saturated soil data at a high frequency so that we can determine the total mass that's in the formation. And that's not groundwater. That's based on groundwater and soil. So when we're talking about having enough treatment in place, that's to treat the total mass that's tied up, in the saturated soil. So that's the power of what the carbon can do for you, because it expedites that actual and upsets the equilibrium, drive that mass off of the soil, which is going to speed up the overall remedial cycle.
Right. And I guess just to add on to that, these are great technologies for managing that flux into groundwater. But the one thing we really, that's difficult for us to control in source areas is what that back diffusion rate may be, depending on, certain factors, depending on contaminant, fraction of organic carbon, for example. And so that would be the only thing I would add on to that.
But to build onto that, Mike, is that's really the power of the product, is the longevity. So once the products are in place, the treatment mechanism is there, no matter what that rate of back diffusion is, you've got something in place to be able to manage that for the long haul.
Oh, yeah, I agree. I'm just making the point that it's not it may not be a fast process.
Yep, I agree.
Derek, I'll go ahead and kick it back to you to go ahead and, or if you want to comment and then go ahead and wrap up. I think we've only got another minute or so.
Sure. I think my last comment to piggyback on what you two just said was, again, this is when we have a saturated condition. So if you've got a potential source or contribution from your vadose zone, you're looking at a combined remedy approach in a lot of cases, whether it's excavation, whether it's some other chemical process. This absolutely needs groundwater, since that's our transport mechanism to work. So these wouldn't be terribly effective in the vadose zone. With that, as Mike said, there are, I can see a couple other questions here we didn't get to. We'll reach out to those of you that included a question that didn't get answered. And I just wanted to thank everyone again for their time. You can see my contact information is on the screen in front of you. Bob Elliott for RPI as well. But anybody within AST and RPI are available to you. You can visit either of our websites, trapandtreat.com for RPI and astenv.com for those of us at AST. So again, thank you all for your time, and I hope you have a great day.